law of viscosity or based on the concept of viscosity. So out of that, ideal fluid means the fluid which does not have any type of viscosity and which is incompressible in nature. That fluid will be called as a ideal fluid. Whereas a real fluid, that means a real fluid means the fluid which is compressible in nature and is viscous. That means which possesses viscosity is called as a real fluid. So here whatever ideal fluid is there, as the name indicate, that will be the ideal only. So it will not exist on the earth surface. That means whatever fluids are available on the earth surface, all the fluids are real fluid. And next one is the Newtonian fluid. Newtonian fluid means the fluid which obeys Newton's law of viscosity. So we have seen the Newton's law of viscosity also. Newton's law of viscosity means shear stress is directly proportional to rate of shear strain. That is called as the Newton's law of viscosity. So if for any fluid, Newton's law of viscosity will be existing, or if that fluid will obey the Newton's law of viscosity, that will be called as the Newtonian fluid. So all the gases, water, benzene, ethyl alcohol, CCl4, hexane, those are the examples of Newtonian fluid. Then non-Newtonian fluid, that means the fluid which does not obey the Newton's law of viscosity. That means the fluid for which shear stress is not directly proportional to shear strain. That will be called as a non-Newtonian fluid. There is a broad classification of non-Newtonian fluid. In the last lecture, though we have covered this slide, classification or broad classification of non-Newtonian fluid we have not covered. That's why purposefully I have taken this slide. So non-Newtonian fluid example will be all the slurries, then gel, polymer solution, blood, printer ink, then toothpaste, greases, paints, then all the biomedical fluid. Those will be examples of non-Newtonian fluid. Actually, this ideal plastic fluid, that is also called as the Bingham fluid, that is also one type of non-Newtonian fluid. In the case of ideal plastic fluid, up to a yield point, the shear stress has a zero value, though there is a value of shear strain. Correct. The shear strain has a zero value, though there is a shear stress exists in the fluid. But after yield point, shear stress is proportional of shear strain. That is called as a ideal plastic fluid. That ideal plastic fluid is also called as a Bingham fluid. Then the next one is the broad classification of non-Newtonian fluid. So non-Newtonian fluid means the fluid which does not obey the Newton's law of viscosity. Newton's law of viscosity means for which the shear stress is not directly proportional to shear strain. So we are knowing the equation of Newton's law of viscosity. That equation is nothing but tau is equal to mu into du by dy. Mu into du by dy. So if you are unable to visible this slide on your mobile, then with the help of a touch screen, you can enlarge your screen. So by making that enlarge here, you can enlarge your screen and you can visible that entire slide. So here Newtonian fluid means if tau is equal to mu into du by dy, then that will be called as a Newtonian fluid. And non-Newtonian fluid means if shear stress is not directly proportional to shear strain. That means if tau is not equal to mu into du by dy, then that will be called as a non-Newtonian fluid. So whatever non-Newtonian fluid will be there, that will be basically of two types. One will be called as a purely viscous fluid. One will be called as a purely viscous fluid, and second one will be called as a viscoelastic fluid. Purely viscous, and second one is the viscoelastic fluid. So out of that, whatever purely viscous fluids are there, those will be called as a time dependent and time independent. Now, what is the basic difference between time independent and time dependent? So, if the viscosity of that fluid, does not changes with respect to time, then that will be called as a time independent fluid. And if the viscosity of that fluid will goes on changing with respect to time, that means as time passes, if the viscosity of that fluid will goes on changing, then such type of fluid will be called as a time dependent purely viscous fluid, which will be the category of non-Newtonian fluid. Now under that time independent fluid, under that time independent fluid, there will be there will be that will be classified into three subgroups. First one will be called as a pseudoplastic fluid. First one will be called as the pseudoplastic fluid. Second one will be called as a diluent fluid, and third one will be called as a Bingham or ideal plastic fluid. So these are the category of non-Newtonian fluid under the time independent subtype. So under that pseudoplastic fluid, the whatever fluid will be there, which will be falling under the category of pseudoplastic fluid. The equation will be tau is equal to mu into du by dy raised to n. So if value of n will be equal to 0, that means that equation will become as a tau is equal to mu into du by dy. So that will be that we might have called as a Newtonian fluid. But here, if the value here in case of pseudoplastic fluid, the value of n is less than 1. Value of n is less than 1. That's why we are calling it as a pseudoplastic fluid. And example of pseudoplastic fluid is nothing but blood, milk. Those are the example of pseudoplastic fluid. Then second type is called as a diluent fluid. Second type is called as a diluent fluid. So in case of diluent fluid, the equation for those diluent fluid will be tau is equal to mu into du by dy raised to n, whereas value of n is greater than 1. Less than 1 असेल तर pseudoplastic fluid, greater than 1 असेल nth value, then that will be called as a diluent fluid. And example of diluent fluid will be butter. So butter will be the example of diluent fluid. And third fluid under that time independent category will be called as a Bingham or ideal plastic fluid. So we are knowing that in case of ideal plastic fluid, up to yield point, though there is a shear stress, then also the value of shear strain is equal to 0. But after yield point, the value of shear stress is directly proportional to shear strain. So here equation will be equal to tau is equal to tau 0 plus mu into du by dy raised to n. Here value of n is equal to 1. So I will not mention that, but you have to keep in mind that in case of Bingham or ideal plastic fluid, value of n is equal to 1. And here whatever tau 0 term is there, tau is equal to tau 0 plus mu into du by dy. Here whatever that is nothing but the value of shear stress at yield point, because we are knowing that in case of ideal plastic fluid up to yield point, though there is a value of shear stress, then value of strain is 0. But after yield point, that is after tau 0 plus something is there. What is that something? That is nothing but mu into du by dy raised to n, whereas n is equal to 1. That means after yield point, shear stress is directly proportional to shear strain. So that will be called as the Bingham or ideal plastic. Will be and sashes, suspension of clay and sashes. That will be the example of Bingham or ideal plastic fluid. Then under time dependent. So time dependent means as time passes, the value of shear stress of that fluid or value of viscosity of that fluid will either go on or will either go on decreasing, depending upon the situation. That will be called as a time dependent. So under time dependent, there will be again two category. First one will be called as a isotropic fluid, and second one will be called as a rheopectic fluid. So under isotropic fluid, the equation is tau is equal to mu into du by dy raised to n plus function of time. So here whatever function of time term is there, that is decreasing term, then and then only that will be called as a isotropic fluid. So decreasing function of t is decreasing. What is the meaning of this? That means here as time passes, the value of viscosity or value of shear stress of that fluid will goes on decreasing. So here if you are going to see the example, that is printer ink, or another example is crude oil. So as time passes, that means after month or after 2 months, the value of printer ink or viscosity of printer ink or crude oil will not be same as that of previous one. So that's why that value will go on decreasing. That's why we are calling this as a hydrotrophic fluid. So another example is another category is called as a rheopectic fluid. Rheopectic fluid means the equation will be equal to tau is equal to mu into du by dy raised to n plus f of t is there. Here whatever function of time term is there, that function of time term is increasing. That means as time passes, the value of shear stress or value of indirectly value of will goes on increasing. So here example is a rare liquid solid suspension. So yesterday only I have told you the example. A rare liquid solid suspension means if you are going to take the example of a coolant which is used to carry out or which is used for pulling the material which is on the lathe machine. So along with that coolant, that chips may get carried out. So if you are going to take the example of that, that will be coming under the category of rheopectic fluid. Then next category is called as a viscoelastic fluid. Viscoelastic fluid, the equation will be equal to tau is equal to mu into du by dy plus alpha into E, whereas alpha is called as a constant, E is called as a elastic limit. So example will be liquid solid combination in a pipe flow. Liquid solid combination in a pipe flow, that will be the example of viscoelastic fluid. So this is the broad classification of non-Newtonian fluid. So most of the time, based on this broad classification of non-Newtonian fluid only, the question may be asked for your GATE exam, as well as that question may be asked for your IES or another competitive exams also. So that question may be, they will provide you the equation, and based on the equation they will ask you find out the type of fluid. Or another question, they will give the type of fluid and they will in the option they will provide the uh, examples of that fluid, and based on that you have to find out the proper example for the proper fluid. Or third type, that will be the matching the pair. So in one side they will provide the names of that type of fluid, and in the another type they will either provide you the examples or they will either provide you the formulas. So likewise question may be asked for GATE exam or for IAS or another competitive exams. Now whatever these types of fluid we have seen, so the these types of fluid may be drawn on a specific chart, or that may be drawn on a chart also. So sometimes for GATE exam or for IAS exam or for another competitive exam, they will give the question likewise. That means they will show you the chart. On y-axis they will provide the value of shear stress, on x-axis they will provide the value of shear strain, that is nothing but du by dy, and they will draw one line on that chart and they will ask you identify the type of fluid. So uh, based on the line or based on the nature of that curve, you have to identify which type of fluid is there based on that tau versus du by dy curve. So here whatever types of fluid we have seen, so that various types of fluid may be drawn on this shear stress versus shear strain diagram. So here I am going to take on y-axis, I am going to take the shear stress, that is nothing but tau. On x-axis I am going to take the shear strain, that is nothing but du by dy. Now here first type is nothing but ideal fluid. Ideal fluid means the fluid which does not possess any type of viscosity and which is incompressible in nature. Now out of that does not possess any type of viscosity. What is the meaning of this? That means value of mu is equal to 0. Value of mu is equal to 0. So here as we are knowing the equation tau is equal to mu into du by dy. As we are knowing the equation tau is equal to mu into du by dy. So based on this I will get the equation as a mu is equal to tau upon du by dy. And this dynamic viscosity is equal to tau upon du by dy. जर आयडियल फ्लुइडला विस्कोसिटी नसेल, विस्कोसिटी नाही याचा अर्थ काय झाला, म्यू ची व्हॅल्यू किती झाली, 0 झाली. जर म्यू इज इक्वल टू टाऊ अपॉन du बाय dy असेल तर म्यूची व्हॅल्यू जर 0 झाली तर त्याचा अर्थ काय होतोय, टाऊची व्हॅल्यू पण काय होते, 0 होते. सो हियर टाऊ विल बी इक्वल टू 0 only. Tau will be equal to 0 for x-axis only. That's why here whatever x-axis of this graph, tau versus du by dy graph, whatever x-axis of that graph will be there, that will be called as the ideal fluid. And as we are knowing that not a single fluid on an earth surface that can be called as the ideal fluid. So here whatever real fluid will be there, whatever real fluid will be there, the nature of a real the any type of graph, any type of graph except x-axis, because whatever fluids are existing on earth surface, all the types of fluids are called as the real fluid. That means Newtonian as well as non-Newtonian fluid will come under the category of real fluid. So here graph of real fluid, any line except x-axis will be real fluid. Whatever Newtonian, non-Newtonian, or whatever broad classification of non-Newtonian fluid is there, that is coming under the category of a. Then next one is called as the Newtonian fluid. Newtonian fluid means the fluid for which shear stress is directly proportional to shear strain. Shear stress, that means tau is directly proportional to du by dy. That means as value of tau will goes on increasing, value of du by dy will goes on increasing in the same proportional. So here if I am going to draw the line, that is nothing but straight line which will be passing through, origin, the straight line which will be passing through origin, that will be called as a Newtonian fluid. That will be called as a Newtonian fluid. And non-Newtonian fluid means the fluid which does not obey the Newton's law of viscosity. That means for which shear stress is not directly proportional to shear strain. That means any graph except this Newtonian fluid graph and ideal fluid graph. Any graph except x-axis and straight line passing through origin, that will be the example, or that will be the graph of non-Newtonian fluid. Now under non-Newtonian fluid there is a broad classification. Under non-Newtonian fluid there is a broad classification. That means here if we consider curve line, we are going to consider this curve line, that is also example of non-Newtonian fluid. If you are going to consider this curve line, that is also example of non-Newtonian fluid. If you are going to consider this line, that is also example of non-Newtonian fluid. This curve line also example of non-Newtonian. So under non-Newtonian there is a various broad classification of non-Newtonian fluid. So first one is the under non-Newtonian there is one category called as the pseudoplastic fluid. So for pseudoplastic fluid, we are knowing the equation tau is equal to mu into du by dy raised to n, whereas value of n is less than 1. Value of n is less than 1. So for pseudoplastic fluid, the nature of graph will be likewise. Graph for pseudoplastic fluid. Second is called as the silent fluid. Silent fluid, we are knowing the equation tau is equal to du by mu into du by dy raised to n, whereas value of n is greater than 1. Whereas value of n is greater than 1. So here whatever this graph will be there, that will be the graph of non-Newtonian diluent fluid. Then third one, we are knowing that ideal Bingham fluid, that is also called as the ideal plastic fluid. That is also called as a ideal plastic fluid. And we are knowing that for ideal plastic fluid, graph is, or equation is tau is equal to tau 0. Tau is equal to tau 0 plus mu into du by dy raised to n, whereas value of n is equal to 0. That means here up to yield point, here this will be called as a yield point. This will be called as a yield point, and value of shear stress at this location will be called as a tau 0. Value of shear stress at this location will be called as a tau 0. So tau 0 plus mu into du by dy raised to n, whereas value of n is equal to 0. That means up to yield point, though you are going to apply the shear stress, then also the value of shear strain is equal to 0. Then also the value of shear strain is equal to 0. But after yield point, value of shear stress is directly proportional to shear strain. That means straight line will be there, inclined straight line. So here after this, the value of shear stress is directly proportional to shear strain. That means in the same proportion, as the value of shear stress goes on increasing, value of shear strain will also goes on increasing. That's why that will be called as the ideal plastic fluid, or that is also called as the ideal Bingham fluid. This is in ideal condition, but in actual condition, here whatever plastic fluid will be there, the nature of graph of plastic fluid will be likewise. So this will be the nature of graph of plastic fluid. So question for GATE exam as well as various competitive exam, so they will only show you x-axis, y-axis. On y-axis they will indicate the tau, on x-axis they will indicate the du by dy, and they will draw any type of line on this tau versus du by dy curve, and based on that line or based on that curve they will ask you identify the type of fluid. That means if they are going to draw the curve line likewise, on the shear stress versus shear strain, then you should identify this curve line is indicating the non-Newtonian pseudoplastic fluid. If they are going to draw the curve line likewise, then you should understand that this line is indicating the nature of plastic fluid. Line likewise, you should understood this is the line which is indicating the non-Newtonian diluent fluid. So now based on this only we have to solve some question. So once again I request you, if you have not brought the pen and paper for each and every FM lecture, you should be along with your pen and paper. Don't use the calci for solving the problem. Take 2 minutes instead of 1 minute for getting the answer. But if you are going to use the calci, then you are going to lose your confidence, because here you will not understand the method how to solve the problem without using the calci, because most of the values which are used in such type of competitive exam, those may be getting cancelled. So until and unless you are not going to make the practice to solve the problems without using calci, it will not be possible to in the final exam, that means in the competitive exam as well as for technical test, it will not be possible for you to solve that question within 1 minute or 2 minutes. But in competitive exam you will get hardly 2 minutes for one question for problem. So first question, match list 1, that is type of fluid, with list 2, that is variation of shear stress, and select the correct answer. So this is the list 1 and list 2, and they have given the option A, B, C, D. So you have to read the problem, you have to read the list 1, list 2, options are provided A, B, C, D, and you have to give the correct answer. Chat box is your answer. You can give the answer in chat box. So here in the list 1, ideal fluid, Newtonian fluid, non-Newtonian fluid, Bingham fluid, and list 2, they have given the various option. Ganesh Kotkar, it is time now. Suraj Gaudi. So most of the students are choosing the D option. So ideal fluid, if you are going to see the D option, then for A option 4, B option 1, C option 2, and D option 3 is there. So if I am going to check the answer D is the correct answer, because we are knowing that ideal fluid means the fluid which does not possess any type of viscosity. Any type of viscosity means value of shear stress is equal to 0. So for A, option 4 should be there. So here you should use the trick in competitive exam, because uh, you are, yes, in the first lecture itself I have shown you the pattern of various competitive exams. So in 2 hours it is necessary to solve 150 question, or one in 1 hour it is necessary to solve 90 question or 100 question. So you should opt the policy, that means eliminate the option. So here, as A, ideal fluid shear stress is equal to 0. So as you are knowing that for A option, fourth option is correct one. So you have to immediately eliminate option A and C, and you have to focus only on option B and D. So here, in case of option B and D, next one is for B, 2 and 1. So B option is non-Newtonian fluid. Sorry, Newtonian fluid. So we are knowing that in case of Newtonian fluid, shear stress directly varies with the rate of shear stress. That means for B, option 1 is corrected one. So thereafterward, not necessary to check the next two option. So you have to consume your time. So here, option D, directly you have to write option D by confirming these two. But while confirming, you should be 100% correct one. But otherwise, if your answer for B is wrong one, then your whole answer will be wrong. Then next question. Here also list 1, list 2, and 4 option. Chat box is open for your answers. Only 5, 6 or 7, 8 students are giving the answer out of 55 students. So this is the question which was asked for IES exam 2003. Don't copy paste the answers, because once if anyone student started writing the C option, then next student. So most of the students are giving the answer as a C. So tau is equal to mu into du by dy raised to n, whereas n is equal to 1. So when n will be equal to 1 for Newtonian fluid, that means for 1, option number 3 should be there. So option number 3 for option A and option C, that option number 3 is there. So you have to eliminate that option B and option D. So out of that two option, one will be the correct answer. Then second, if you are going to check, the second one is whereas n is less than 1. Now here you should be 100% clear that when the value of n is less than 1. So we are knowing that in case of pseudoplastic fluid, the value of n is less than 1. That means for second one, that means for B, option number 4 should be there. That means here option number C is the correct answer. Are you getting? So option C is the correct answer. Then next, whether screen is visible to everybody? Yes or no? Anyone?
Yes, sir.
Whether screen is visible?
Yes, sir.
Hello?
Yes, sir. It is visible.
Whether screen is visible?
Yes, sir,
Yes,
it's
sir. It is
visible.
visible.
Wait. Hello?
Yes, sir, yes, visible.
Yes,
Okay.
sir, screen is visible.
Okay. So next question. In an experiment, the following shear stress time rate of shear strain values are obtained for a fluid. Time rate of shear strain, that is 1 upon S, shear stress in kilopascal. This is the question which was asked in the GATE 2000, sorry, IES 2008. So you have to find out the type of fluid based on this graph. They have given the values of shear stress in terms of kilopascal and time rate of shear strain, that is called as a shear strain or rate of shear strain. Time rate of shear strain is also called as a rate of shear strain. So here you have to identify the type of fluid based on this chart. Chat box is open for you. Methane fluid, Bingham fluid, sorry, Bingham plastic fluid, pseudoplastic fluid, diluent fluid. So ABCD. Give the answer, remaining student. 55 students are there. I am getting hardly 5 to 6 reply or maximum of 2 reply. I will wait for some time. I want maximum reply from your side. Remaining student, there is no problem. D D A C C A C A A D A D. So here various answers are coming. Remaining student, you have to also participate. Only maximum of the 10 answers are. So what will be the correct answer? Everybody's answer is correct. That will not be the case. So correct option is option D. That is nothing but diluent fluid. Fine. Anybody? Here they have provided the values. So whatever these types of fluids are there, we can identify the types of fluid based on the graph of shear stress versus shear strain also. So here, if you are going to draw the graph of shear stress versus shear strain, then for zero value of shear stress, we are getting the value of shear strain as a 0. Then for if value of shear stress is 1.4, so for 1.4, you are getting the value of shear strain as a 2. If value of shear stress is at 2.6, you are getting the value of shear strain as a 3. And if value of shear stress here directly for value of shear stress 4, you are getting the value of shear strain as a 4. So for 4, you are getting point here. So whatever your nature of graph will be there, that nature of graph of shear stress versus shear strain will be likewise. And such type of graph will be called as a diluent fluid. Such type of graph will be there for a diluent fluid. So option D will be the correct answer. Are you getting? Now, next phenomenon is called as a surface tension. So, we are knowing the definition of surface tension. So, what is the surface tension? Will tell anybody? Shailesh Pawar. Hello? Shailesh Pawar. Is Shailesh Pawar is there? Shailesh Pawar. So, it is being observed that most of the students are joining the lecture at the end of lecture. That means in the last 10 minutes or 15 minutes for attendance purpose. So afterwards, शैलेश पवार आहे का शैलेश पवार?
बोला की
So
सर.
you have to join the lecture. किती वाजले?
लक्षात.
हा? So you have to take care that here afterwards you have to join the lecture at the that start of lecture only. Don't join the lecture at the end of lecture. So surface tension. We are knowing the definition of surface tension, that is nothing but the tensile force acting on the surface of liquid in contact with gas or in contact with the another immiscible liquid such that contact surface behave like a membrane under tension. So if you are not understanding the concept surface tension with the help of this definition, so you can understand that concept of surface tension with the help of this diagram. So suppose you are having one bucket, or suppose you are having the water in one container, and if you are going to consider any three fluid particle from that water, suppose this has a fluid particle A which is completely surrounded by the same fluid particle. This has a fluid particle B. So maximum portion of this fluid particle is surrounded by the same fluid particle, but small portion is surrounded by the air. That means here immiscible liquid is there. That means immiscible fluid is there. That is called as a liquid and gas interface is there. Here, if I am going to consider the point C, so here 50% of point C is surrounded by the same fluid, and remaining 50% portion is surrounded by the air. So here, if I am going to consider the point number A, here if I am going to consider point number A, as that point number A is surrounded completely with the same fluid. So there will be two types of forces. First one will be called as a cohesive force. Second one will be called as a adhesive force. So cohesive force is nothing but force of attraction between two similar molecules. Two similar fluid molecule will be called as a cohesive force, and adhesive force means force of attraction between different fluid molecule will be called as the adhesive force of attraction. So here, if you are going to see the example of point A, as point is surrounded by the same fluid molecule surrounding to that fluid particle A, same fluid molecules are there. So here, attraction in all the direction, that is cohesive force in all the direction will be same. Because of the same, here net force acting on molecule A, or net effect net force effect acting on molecule A will be equal to 0. But here, if you are going to consider the point B, or fluid molecule B, so here maximum portion of fluid molecule B is surrounded by the same fluid, and minimum portion is surrounded by the another liquid or another immiscible fluid. So here gas is there. So here this will be there. This portion will be attracted by the surrounding fluid molecule by the force action called as the cohesive force. Smaller portion will be there. This smaller forces will be this smaller forces will be attracted by the adhesive force. So here, as value of cohesive force, adhesive force. So net effect acting on a fluid molecule B will be the force which is acting in the vertically downward direction. Similarly, if you are going to see the point molecule C, fluid molecule C, here 50% is adhesive force, remaining 50% is cohesive force because of same fluid molecule. That part of the molecule C is because of the air, that is air liquid interaction, air liquid fluid molecule force of attraction will be there. So here cohesive force value will be greater. So here net force acting on the fluid molecule C will be equal to, or will be in the vertically downward direction. So here, as we have seen that fluid molecules which are on the surface, which are on the free surface of that fluid molecule or on that fluid, all the fluid molecules are having the net force in the vertically downward direction. And same here, whatever top surface of will be there, that will be the under tension. That means that top surface of the fluid will act like a membrane which is under tension because of the tensile forces acting in the vertically downward direction between the surface of liquid and surface of gas. So that force acting on the surface of the liquid, that will be called as the surface tension. So here whatever surface tension phenomenon is there, that surface tension phenomenon mainly caused because of the cohesive force of the fluid at the surface of the fluid. So you have to keep surface tension phenomenon is mainly caused because of the cohesive force between the fluid molecule at the fluid surface. And SI unit of surface tension is nothing but Newton per meter. So whatever these two points are there, those are very much important as far as your competitive exams are concerned. So first one, surface tension is caused mainly because of the cohesive force. SI unit of surface tension is nothing but the Newton per meter. Though we are saying that here surface tension is nothing but the tensile force acting on the surface of the fluid. So tensile force will be indicated in terms of Newton, and top surface, that top surface will be measured in terms of meter. So SI unit of surface tension will be Newton per meter. Are you getting? Now here the important point as far as GATE exam as well as IAS exam or another various competitive exams are concerned. So most of the time they will ask you find out the surface tension or pressure difference acting on a liquid droplet, acting on a water bubble, soap bubble, or acting on a liquid jet. So here we have to find out surface tension on a liquid droplet. We have to find out surface tension on a liquid droplet. So for that purpose, if I am going to consider the liquid droplet, suppose this is a liquid droplet. So here whatever liquid droplet will be there, that liquid droplet will be spherical in shape because of the surface tension. Because here whatever outer surface of this liquid droplet will be there. So here complete outer surface of that liquid droplet will be the liquid air interface, will be the liquid air interface. Because of this liquid air interface, there will be the tensile force acting on the outer surface of the liquid droplet, and because of the same only the liquid droplet will be spherical in shape. And because of the same reason, whenever you are observing that water droplet which is coming out of the sorry uh, when there will be the rain, then you will observe that whatever water droplets are coming towards the earth surface, those will be in the spherical shape. So here, if I am going to consider this as a water droplet on which is having the d as the diameter of that water droplet, if I am going to consider the sigma is nothing but the surface tension acting on the liquid droplet. Sigma is nothing but the surface tension acting on a liquid droplet. P is nothing but the pressure intensity inside the liquid droplet. Then here, if I am going to cut this water droplet, that means from here, then that water droplet will be look likewise. So this is the half portion of water droplet. So here, whatever this circumferential area is there, whatever this circumferential area is there, on this circumferential area, that means here, this is nothing but the interface between liquid droplet and air. This is nothing but the interface between liquid droplet and air. And as this is the interface between liquid droplet and air, that's why here tensile force will be acting. That's why here tensile force will be acting on this circumferential area. So here, if I am going to calculate tensile force due to surface tension, if I am going to calculate tensile force due to surface tension acting from the circumference of the cut portion, then that tensile force will be equal to. So here, sigma is nothing but shear stress or surface tension. So sigma into circumference. Sigma is nothing but surface tension So sigma into circumference, that is nothing but the tensile force due to surface tension acting around the circumference of the cut portion. So here circumference is nothing but, here you have to consider this much area. So circumference is nothing but pi into d. So tensile force acting on the water droplet is nothing but sigma into pi d. Is nothing but sigma into pi d. Now on the same portion, sorry, on the same liquid droplet, another force will be acting. So here if I am going to draw the free body diagram, so here another force will be acting on the same area, and that another force is nothing but the pressure force. So here this is the same portion. So here, as on the liquid air interface, surface tension force is acting. So on this liquid droplet here, inside this liquid droplet, there will be the pressure forces. And here if I want to calculate the pressure forces acting on this liquid droplet, then pressure forces acting on this liquid droplet is nothing but pressure intensity P into area of this liquid droplet. So pressure intensity P into area of this liquid droplet is nothing but pi by 4 d square, because small d is the diameter of that liquid droplet. So P into pi by 4 d square, that is nothing but the pressure force acting on this liquid droplet. So for equilibrium condition, both the forces will be equal. That means tensile force due to surface tension acting around the circumference of the cut portion, and pressure force due to on the area pi by 4 d square, both the forces will be equal. So if I'm going to equate both the equation, that means sigma into pi d is equal to P into pi by 4 d. Here I will get that here pi will get cancelled, and I will get the value of P. So value of P will be equal to 1d, and here 1d will get cancelled. So P is equal to sigma into pi d divided by pi by 4 d square, which is equal to 4 sigma upon. So this is the value of pressure intensity. This is the value of pressure intensity which is acting on a liquid droplet. So you have to keep in mind that the value of pressure intensity is 4 sigma upon d, whereas sigma is called as the surface tension, d is called as the diameter of the liquid droplet. Similarly, we have to find out the surface tension acting on a hollow bubble. We have to calculate of surface tension acting on a soap bubble or hollow bubble. So here also, whatever bubble, hollow bubble is there, that is also spherical in shape. The bubble is there, that is also in shape. So here, if I'm going to consider D is the diameter of liquid, hollow bubble. P is nothing but the pressure intensity inside the droplet. Sigma is nothing but the surface tension of the liquid. So similarly, here, if I'm going to take the cut portion of this liquid droplet, not liquid, if I'm going to take the half portion of this hollow bubble, so here surface tension or tensile force acting on this hollow bubble will be, now in the previous case there was the liquid droplet. Liquid droplet means whatever inner portion was there, inner portion was full of that same liquid droplet. But here, as this is the hollow bubble, so here this is the liquid film, but inside this there is the air, as well as outside there is the air. So we are knowing that whatever surface tension phenomenon, that surface tension phenomenon is acting at the interface between liquid and air. So here 2 times surface tension will be there. That means here whatever outer portion is there, this outer portion and outer air, that is liquid air interface, here surface tension is acting, and at the inside also, because this is the liquid droplet or liquid film, and inside, as this is the hollow bubble, so inside this also there is a liquid air interface. So here in this case, tensile force due to the surface tension acting on the circumference of the cut portion, that will be equal to, here whatever surface tension we have to consider that surface tension at the outer edge as well as at the inner edge. So twice into sigma into pi d. That means sigma into circumference was there in the liquid droplet, but here as value of sigma is twice, and at the outer also there is a liquid interface. So at liquid air interface, at inner liquid air interface, that's why I have to consider twice sigma. In case of liquid drop, there was only one liquid air interface, that is at the outer portion. Here inside was liquid itself, so here twice into sigma into pi d. Similarly, here if I want to calculate pressure forces, if I want to calculate pressure forces acting on a hollow bubble, then pressure forces acting on a hollow bubble on this area will be equal to pressure intensity P into this area is nothing but pi by 4 d square. So P into pi by 4 d square. So for equilibrium condition, I have to equate this equation with this equation, that is P into pi by 4 d square is equal to twice into sigma into pi d. So here also pi pi will get cancelled, dd will get cancelled, and I will get the equation for P, that is pressure intensity acting on a hollow bubble, that is but 8 sigma upon d. Pressure intensity acting on a hollow bubble is nothing but 8 sigma upon d. Pressure intensity acting on a liquid droplet, pressure intensity acting on a liquid droplet, that was 4 sigma upon d. That was 4 sigma upon d. And based on this equation, you are able to calculate the surface tension acting on a liquid droplet as well as acting on a hollow bubble. So here surface tension acting on the hollow bubble, that is nothing but value of sigma will be equal to P into d upon 8. And in case of liquid droplet, value of sigma, that is nothing but surface tension is nothing but P into d divided by 4. Are you getting? Yes or no? P into d divided by nothing but the surface tension acting on a hollow bubble, and d divided by 4, that is nothing but the surface tension acting on a liquid droplet. Now my question is, in which case the value of surface tension will be lower, in case of hollow bubble or in case of liquid droplet? You can use the chat box. My question is, in which case the value of surface tension will be lower, that is in case of hollow bubble or in case of liquid droplet? What is the answer? I will repeat the question. In which case the value of surface tension is lower of liquid droplet or in case of hollow bubble? That is value of sigma for liquid droplet, value of sigma for hollow bubble. So in case of hollow bubble, value of will be lower, and that will be 50% of the surface tension as that of liquid droplet, because we are knowing that sigma for bubble is nothing but PD upon 8, whereas sigma for liquid droplet is nothing but PD upon 4. Just 30. Simple application. Whenever you are washing your clothes, you are using the soap for washing the clothes, that is detergent or soap. Why you are using the detergent or soap? Because whenever you are using the detergent or soap by washing your clothes, at that time, because of that detergent or because of that soap, there will be the formation of hollow bubble. There will be the formation of hollow bubble, and as there is a formation of hollow bubble, that's why surface tension, that is nothing but tensile force acting on the surface of that cloth, will goes on decreasing. As surface tension on the cloth surface is goes on decreasing, that's why whatever dirt particles are there, those will be easily removed from that cloth. That's why while washing the clothes, you are using the detergent or you are using the soap. Main reason is this derivation. Because by using this derivation, you are getting that surface tension is nothing but 3D upon 8 in case of hollow bubble, whereas in case of simple water, that is liquid droplet, 3D upon 4. So 50% reduction of surface tension will be there in case of hollow bubble. Are we getting? What is the time now? Time is 5:03. So shall we stop or one more derivation shall we take? What we have
Sir,
to do?
today we are stop here.
Huh?
Stop here.
Today? Okay, we have to stop here. So
Sir,
wait, I'm going to wait. I'm going to generate the attendance. Now, बोला.
sir, feedback of ETT.
Feedback of ATT. What happened?
Some students
Okay, you can.
are giving feedback.
Some student want to give the feedback related to ATT.
Yes, sir.
Okay, give the feedback. No problem.
Shraddha.
Hello? Hello?
गेले
Hello.
काय सर?
आहे बोला.
Sir,
Hello?
lecture should be reduced.
Lecture should be reduced. Why?
Yes, sir. Sir, it is too much like 5 hours, sir. Means we are constantly using the phone. So it is not possible for us, sir.
Okay. Any another? I'm not going to take the, as you are knowing that I am not the final authority to take the decision. I will only convey your message to our HOD as well as Dean TPI. Sorry, Dean TPI. Any another?
घरचे अलाव करत नाही तेवढ्या फोन यूज करायला सर.
कशासाठी करत नाही? श्रेयश चव्हाण. अजून कोणाचे आहेत का घरचे? कोणाच्या घरचे अलाउड करत नाही त्यांचे मला नाव सांगा, मी घरच्यांना कॉल करतो तुमच्या.
सर
कोण कोण आहेत? श्रेयश चव्हाण. अजून?
सर 5 hours फोन घेऊन बसायचं म्हणलं तर डोळे पूर्ण दुखतात सर. अगोदर स्पेक्स आहेत आणि त्यात 5-5 तास फोन घेऊन बसायचं म्हणजे पॉसिबल नाहीये.
बर.
सर 3 hours सफिशियंट आहेत.
3 hours sufficient. अजून कोणाचं आहे? काय करूया आपण? हॅलो.
हा सर.
काय करू, तुमच्यातले ए डिव्हिजनचे 8-9 मुलं आणि 8-9 नको, ए डिव्हिजनचे पर बॅच 2 म्हणजे 8 आणि बी डिव्हिजनचे पर बॅच 2 असे 8 आणि 8 16 मुलं अलॉंग विथ HOD अँड डीन TPI आणि बाकीचे फॅकल्टी कोण असतील तर ते फॅकल्टी आपण काय करू, एक मीटिंग शेड्यूल करूया. त्यामध्ये तुमचे जे काय मुद्दे असतील ते तुम्ही पुटअप करू शकता आणि त्यानुसार मग HOD सर किंवा डीन TPI जो काही डिसिजन घेतील तो फायनल डिसिजन असेल.
हॅलो सर. सर
बोला.
सर ते आता तुम्ही ते टेस्ट सिरीज वगैरे सबमिट करणार सर. आता हे 5 तासांनी मोबाईल वगैरे बसल्यावर मग परत ते टेस्ट सिरीज कधी द्यायचं सर? आणि परत आमचा कोर्स पण आहे.
कोर्सेरा त्यासाठीच आपण काय करू शकतो, आता ऐकून घ्या. तुम्हाला पण माहित आहे फायनल डिसिजन मी घेऊ शकत नाही, मी फक्त मेसेज तुमचा कन्वे करू शकतोय. त्यामुळं मी काय करतो, डीन TPI आपले HOD सर त्या दोघांच्या कन्व्हिनियंट वेळेनुसार तुम्हाला टायमिंग सांगतो कधी असेल मीटिंग. आज तर पॉसिबल नाही, उद्या किंवा परवा 2 दिवसात आपण ती मीटिंग घेऊया. मग त्यात तुमचे जे काय प्रॉब्लेम असतील, आता कारण की तुम्ही 1 आठवडा तर ट्रेनिंग केलेलं आहे त्यामुळे तुम्हाला थोडाफार एक्सपिरियन्स आलेला आहे ट्रेनिंगचा, बरोबर आहे. त्यात तुम्हाला जे काही प्रॉब्लेम फेस झालेले आहेत ते तुम्ही पुटअप करू शकता. मग त्यानुसार डीन TPI आणि HOD सर दोघांमध्ये डिस्कस करून जे काही डिसिजन देतील ते फायनल असेल. फक्त तुम्ही काय करा, बॅच वाईज प्रत्येक बॅच मधले 2 जण कोण बोलणार किंवा कोण मीटिंग अटेंड करणार ते तुमच्या डिसाईड करा. कारण की सगळ्या फोरम बरोबर डिस्कशन करणं ते पण पॉसिबल होणार नाही. चालेल.
ओके सर.
काळे सर
येस सर, ओके.
हा
काळे सर
हा बोला दिग्विजय सर.
हा, तर ते चव्हाण सरांशी बोललोय मी एक रिव्ह्यू मीटिंग घ्यायला. तर
बर.
आज ते म्हणजे संडे असल्यामुळे आज घेता येणार नाही, तर उद्या एखाद्या वेळेस घेतील.
चालेल,
हेच
तेच बोललो
एकंदरीत
मी.
ATT रिव्ह्यू कसं चाललंय,
हा
काय
कारण की
चाललंय, किंवा मुलांचे
आता
काय
काय झालं
प्रश्न असतील.
दिग्विजय सर, आता एक
हा
आठवडाभर मुलांनी म्हणजे आपलं ATT अटेंड केलेलं आहे, त्यामुळे त्यांचं म्हणजे फीडबॅकच्या स्वरूपात आपल्याला एक मीटिंग घ्यायला पाहिजे. त्यात त्यांचे जे काही पॉईंट असतील आपण आता HOD सरांना पण बोलवू आणि मोठे सरांना पण बोलवू TPO ला. मग ह्यांचे मुलांचे जे काही पॉईंट असतील ते मुलं पॉईंट मांडतील आणि HOD सर किंवा मग डीन स्टुडंट म्हणतोय आपले TPO जे काही डिसिजन घेतील तो फायनल असेल शेवटी.
चालेल ठीक आहे.
तर आपण काय करू, आता तुमचा जो फीडबॅक आहे तो मी HOD सरांशी आणि मोठे सरांशी डिस्कस करतो. त्यानुसार त्यांच्या कन्व्हिनियंट वेळेनुसार आपण मीटिंग शेड्यूल करूया. फक्त तुमच्यात डिसाईड करा पर बॅच 2 स्टुडंट पाहिजे. कारण की स्ट्रेंथ जर जास्त झाली तर त्या केसमध्ये पर्सन टू पर्सन सरांना पण बोलता येणार नाही आणि तुमचे पॉईंट पण समजणार नाही. त्यामुळे ऍज अ रिप्रेझेंटेटिव्ह पर बॅच मधून 2 स्टुडंट झाले तरी सफिशियंट होतील. ते तुमचे पॉईंट पुटअप करतील. त्या मीटिंगच्या डिस्कशन थ्रू जो काय फायनल डिसिजन येईल तो आपण इम्प्लिमेंट करूया. चालेल.
हा, येस सर. ओके सर.
चालेल.
ओके, थँक्यू सर.
थँक्यू फॉर अटेंडिंग द मीटिंग. So we'll arrange that meeting soon. Probably tomorrow or day after tomorrow. Within 2 days, I will arrange that meeting, and I will convey the message accordingly.
येस सर.
Okay, thank
ओके,
you.
थँक्यू सर.
Now you can leave the. Okay, thank you.
हॅलो. हॅलो. हॅलो.